So, good morning, everyone. I am thankful to our top leadership, Honorable Chancellor and Founder, Pro Chancellor, Vice Chancellor, Director HRDC, and Dean Faculty of Science to allow us to organize the Faculty Development Program on current trends in theoretical and experimental research in physics under the aegis of Human Resource Development Center, Integral University. Today is the fourth activity of the lecture series of the Faculty Development Program. It is my honor to introduce the distinguished speaker and a resource person, Dr. Faraz Ahmed Inam, Associate Professor, Department of Physics, Aligarh Muslim University. Dr. Faraz joined AMU in February 2014. His background ranges from solid-state nano-optics, spectroscopy, to quantum optics of single photon sources. He has worked on both experimental and computational aspects to these problems. He has more than 10 years of experience in academic and research. He did his BSc at University of Delhi, MSc from IIT Kanpur, MTech from IIT Delhi, PhD from Macquarie University, Australia. He also worked as visiting scientist at TFI Mumbai, postdoctoral researcher at Max Planck Institute of Biophysical Chemistry, Germany. Dr. Faraz received rupees 1.1 crore under the DST FIST and DST CRG grants. Also, UGC startup grant of rupees 66 lakhs. He is now in the process of establishing a sophisticated experimental facility capable of performing quantum optics experiments at the single photon level in AMU. Dr. Faraz visited Harvard University, USA, HP Laboratory, USA, Melbourne Material Research Institute, Australia, Max Planck Institute of Biophysical Chemistry, Germany. With this brief introduction, let me invite Dr. Faraz to deliver the FDP lecture. Sir, please.
Thank you, Dr. Shah Alam. Thank you for the introduction. Uh, hello everyone. Good morning, everyone. So today, as you all see, I have chosen a very fundamental and important topic about light. What light is. Like my field of research is understanding the light-matter interaction at the deep into the quantum level. When we treat both light and matter in the quantum picture. So, but before understanding, we should know like how the understanding of light evolved with time and what actually light is. Even Einstein in a quote has said that he devoted almost half of his last part of his life to the understanding of light, and he himself doesn't know exactly what light is. And he tells in his own words that today every layman thinks that he knows the answer. So let's start with the beginning, the evolution of the understanding of light, what light is. So all of you would be aware about in your schools about the Fermat principle, that light travels in straight lines. The light travels and the time it takes is the extremum time taken by it, and the extremum time leads to straight line paths. And like back into the 16th century, 17th century, the phenomena which were observed were in general refraction of light. Like you don't have to observe interference and other things. You require the light waves to have to be in phase with each other too. So by at that time the things were not evolved, and the first theory about explaining the concept of light was originated or given by Newton. Newton was a well-known scientist in his time, and he gave the corpuscular theory of light. His thought or his imagination was waves travel like when you put a stone in water in a pond. How you see that waves travel as ripples and they die down. But from the Fermat principle, which shows that light should travel, follow a straight line, the laws of reflection, which were meant to be in straight line at that time, from Fermat principles. So Newton, just without any deep thought or without any deep sort of backing to his theory, he just gave a theory, corpuscular theory of light, where he treats that light a particle, corpuscles, which particle always travel in straight lines. So you hit a particle, throw a particle, it travels a straight line. If there is no force as such. So what he came up with the corpuscular theory of light. And around the same time, there was another great physician or scientist. At that time, it was all philosopher. We like tell them, because Newton itself was a mathematician, was a physicist, was a philosopher, was a thinker. So similarly, there was Christian Huygens at his time. So Christian Huygens was also a mathematician, a physicist, a philosopher. So he wasn't able to understand or to digest the corpuscular theory of light, that light behaves as particles, and he himself gave the wavefront theory of light, which all of us know now, the wavefront theory of light. And Christian Huygens, you have Huygens wavelets, Huygens fringes out of it. So Christian gave the wave nature of light, the wave theory of light, but the the status of Newton was much bigger compared to Huygens at that time, and people for almost 100 years or so believed in the corpuscular theory of light given by Newton. So it was, the things were going as such, and people were depending on the Newton's theory of light. But what happened, that in 1803, around 140 years after Newton gave the corpuscular theory of light, 143 years after, then Thomas Young, using a double slit, same source of light, two double slits at same distance from the source. So what you have at the same source A and B, you have the waves coming there from the source are in phase with each other. So when you have two sources in phase with each other, you will get interference pattern. And so Christian Huygens, in the experiment, he shows the interference pattern of light. And interference is a phenomena which can't be explained by the particle nature. So Christian, like Thomas Young's experiment, was the basic, like the first or experimental evidence which showed that light, which shows phenomena like interference, can't have a particle nature. So the understanding came up that light should have a wave nature now. If interference is happening out of light, then the light needs to have a wave nature, and only when the wave are in phase with each other, they lead to maxima. Out of phase with each other, they lead to minimas, and you get fringes in on the screen. When you had this at the screen where you record the film or record the pattern, you get interference fringes. So interference phenomena leads to the wavelength explanation of light. But then the thing was, if light is a wave, then what are the things which are oscillating? Before that, you have water waves, where what is the water particles are oscillating. You have sound waves, where pressure is oscillating, vibrating. But then, if light is a wave, and since light is traveling, say in the atmosphere, which is just empty, say light coming from the sun to us on Earth, what is in between? It's empty universe. So if it's empty universe, what are the things which are oscillating? Then people came up, the scientists came up with, like, this was the time when the things were evolving, the physics was evolving, and scientists came up with the idea of ether. All of you would be aware that the idea of ether, and then Michelson Morley did the experiment to prove the ether medium. But we all know that the outcome of that experiment was negative. They observed that in whatever direction with respect to the motion of the earth the light was traveling or coming, the speed of light remains constant. The speed of light was not dependent on the on reference to the object, the velocity of the object. The speed of light remains constant. So people were amazed or didn't knew, were thinking about what's the thing which is vibrating. If light is a wave, what are the things which is vibrating? What are the things which are vibrating? So to answer this, Maxwell, based on the Faraday's law, in 1860 he came up with the mathematical explanation, mathematical theory of electromagnetic waves. And the theory of electromagnetic waves evolved from the time when Maxwell gave his explanation. We all are well aware about the Maxwell's equation, the four famous Maxwell's equations. And what those equations tell us, that propagation, for light to propagate, it doesn't require any particle, anything to vibrate. It's the self-propagating electric field, and the vibrations of electric field, oscillations of electric field will give rise to a changing electric field, will give rise to a magnetic field. A change in magnetic field will give rise to a electric field. So all are self-like, self-dependent on each other, and the motion of one electric field will give rise to the motion of magnetic field, and simultaneously, and they propagate, and the propagation happens in a direction perpendicular to both the fields. So now the things are becoming more clearer that what light is. Light is an electromagnetic wave, and where electric and magnetic fields are vibrating perpendicular to the direction of motion of light. So till now in the classical theory, things are well developed, and we have the classical theory of light given by Maxwell, explaining interference, explaining diffraction, explaining both reflection, refraction, almost all phenomena till now. So everything is very nicely explained, things are very nicely beautiful, everything. But what happened next? Like this was the evolution time of like development of physics, or you see. Then in like what happened at 1900, just the starting of the 20th century, what happened? The black body experiment was done, black body radiation. And if you see the spectrum here, what you see as the temperature of the object of the black body is increased, what happens? That the intensity of the emission increases. This is explained by classical theory. This can be easily explained. That if you increase the temperature, more number of particles will be vibrating. Like if light is emitted by dipoles in the classical picture, radiating dipoles. So dipoles radiation will increase, the oscillation will amplitude, dipole oscillation amplitude will increase. The increase in dipole oscillation amplitude will result in more field, intensity of the field will increase, and you will have more intense light coming out from dipole radiation. So classically it's explained. But the interesting thing happened is that it's not only that the intensity is increasing. If you observe carefully in the figure, you will see as the temperature is increasing, the peak of the emission is shifting towards lower wavelength or higher frequency. But in classical theory, the frequency is not dependent on intensity. Frequency should not depend on the amplitude of vibration. So to explain this, why the frequency is shifting when we have higher temperature, Planck came up with the idea that, leave the classical theory, he came up with the idea that light is emitted as particles known as photons. And these photons have energy associated as given by proportional to frequency. And the proportionality constant in honor of Planck was named as Planck's constant, because he was the one who gave the first idea about photons. So what we are back to particle theory. What Newton first gave, the corpuscular particle theory of light, Planck gave back like Then the physics was evolved. We got interference pattern, diffraction pattern to explain that the development of Maxwell's equation came into, and then the electromagnetic theory of light came into. But Planck, to explain the black body radiation, he again went back to the particle nature of light, where he told that light is emitting as particle known as photons. He gave the particle name as photons, and the energy of the photon is dependent on frequency. But here there is a catch. The photons energy, photon though is a particle, but its energy is dependent on frequency. And frequency is a wave character. How will you associate a frequency with a particle? Frequency or wavelength are associated with a wave. So he gave the explanation that the light is emitted as photon, but he stopped at that point and he told that because all the physics were known in terms of electromagnetic theory, classical electromagnetic theory was well established. He told that though Planck just told that though light is emitted from the black body as photon as particle, but they travel as waves. He wasn't bold enough to tell that the light is emitted as particle as photon and they travel also as photon. He did because of the well established nature of electromagnetic theory, Maxwell's equation at that time. So he stopped at that point. But just few years, 5 years after that, to explain the photoelectric effect, to explain what's photoelectric effect, all of you know of. When light strikes a metal, then electrons are emitted out of the metal, and you can measure if you put it in a circuit, a current is generated. So photons are resulting in the emission of electrons. And it was observed that even if you have photons of wavelength less than certain frequency, or you have photons less of energy, but they travel as waves.
I think Faras's internet has been gone.
Yes, connectivity problem. I think we should wait for a few minutes. Then you can call.
Hello,
I
sorry
think
everyone, internet disruption here.
yes, yes.
Okay, I'm using mobile data now.
Okay.
Okay.
just below present.
Yeah.
Okay, 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 okay.
Is it visible?
Yes, sir. Is it visible? This is visible.
Visible. It's in the.
Not in full screen.
Not in full screen. Okay. Just a minute. Uh, Last time I uploaded the slides. Are they there?
Yes, sir. Yes, sir. They are here. We can see on the screen. Or should I remove that one? You are uploading again.
Yeah, please remove. I will upload again.
Okay. Let me remove it. Okay, I have removed. It's uploaded or not?
Remove.
Yes. Yeah.
Okay.
Yeah. Now we can see at full screen.
So I was at this point.
Yes.
Sorry, everyone.
No problem, sir.
So, so in the photoelectric effect I was talking about, what was observed and was that if light of very dim intensity but frequency above a certain threshold frequency strikes the metal, so the current is detected. A current, small current is detected. But if you have a high intense light, but frequency is lower than the threshold frequency, you don't observe any current. So from the electromagnetic theory, the classical electromagnetic theory, the energy is dependent on the intensity. Energy is dependent on the intensity, and the current should be proportional to the intensity of light and not on the frequency. So here the Einstein, to explain this, the concept of photoelectric effect, what Einstein did, he used the Planck's theory, where Planck told that the light is emitted in terms of photons of energy h nu. He just like came up with the bold idea. He told, or he at that time told, and he sort of uh, argued with the well-established wave theory of light, electromagnetic theory of light, that light not only is emitted as packets of energy known as photons, but it also travels as packet of energy known as photons. And when it strikes the metals, it strikes it as a packet of energy known as photons. And these photons, when their energy is above certain frequency or the threshold frequency, threshold energy, because energy is not dependent on frequency. So if the energy is, or the frequency of light is above the threshold frequency, then you will get current out of it. The photons will give its energy to the electrons, and electron will result in current in them. So Einstein explained the photoelectric effect, taking into picture the photon theory of light, which is a particle theory of light. Point of light, that point of light energy seems particle light. So now we are back to the old thing, that light is a particle. But then the thing was, then what about the other phenomena? About the interference, about the diffraction, which were not, it can't be explained in terms of particles. So Taylor, after that, in 1909, he did an experiment where what he did, he used a very dim source of light such that in a double slit, you have at a time only one photon striking the slit. So at a time, at an instant, if only one photon will strike the slit, what he observed that if he left the experiment to evolve, he observed a interference pattern. He observed an interference pattern on the film there, which he developed. So what's after this? What idea? Like though light is emitted in terms of photon, but photons are evolving as a wave. So what happens that it would seem that the basic idea of quantum theory is the impossibility of imaging an isolated quantity of energy without associating with it certain frequency. But now, why is the photon behaving or the light is behaving as a wave? Because here, if you see the Planck's explanation of light, the photon has a frequency associated with it. And with the frequency, it has a wave nature if you treat, in other sense, if you treat, it has a wave nature associated with it. So light is not just a particle emitting as a photon, but photon itself has a wave associated with it in the explanation that its frequency, its energy is directly proportional to its frequency. So since it has a frequency, it has a wave nature associated with it, and that wave nature is resulting in an interference pattern as seen by Taylor GIT. So at that time, what happens? The quantum physics was evolving, and Louis B. Broglie, he came up. He reasoned that as light are particles but behaving as wave, then he came up. Then there should be a duality for all. Light are particles. There are other particles also. So all particles then should have a wave associated with it. And his duality principle that particles should also have a wave nature associated with them. And to prove this, Davison and German did the experiment of electrons, and they showed in from Davison German experiment that electrons also have a wave nature. In the Compton experiment also, the wave nature was explained. So the things are evolving, and if we started with from the pure theory from the Newtons that light are just particles, nothing else, corpuscles. Then from the electromagnetic theory, that light explanation after the Young's double slit experiment explanation that light shows interference and then diffraction. Then these experiments can't be explained without the wave nature of light. And then after that in 1860s, the development of the Maxwell's theory of light, the electromagnetic theory of light, everything was well established as light to be a classical electromagnetic wave. Then things started changing in 19 in the beginning year of the 20th century. The Planck came up with the black body explanation for the black body radiation in terms of light being a particle known as light emitted by a black body, radiation body as particles in terms of particles known as photons, but photons he associate a frequency with the photons. And Einstein came up with another bold explanation that light not only are emitted by the body as photons, they also travel in space as photons. So then to prove that, like to see whether these single photons, though they are emitted as photons particles, but since interference is well known established experiment, can these photons results in interference? So the Taylor experiment with one photon with very dim source of light such that only one photon striking the slit at a time, he he showed that this photon concept of light will also give rise to interference pattern. So it has a sort of wave nature also associated with it. And de Broglie then came up that if light is a particle and has a wave associated with it, then why not other bodies? They could also, like particles, could also have a wave associated with it, like electrons. And then Davidson German proved his experiment, his theory of. So to explain all this, then Heisenberg came up like which nature is seen where. Sometimes we are talking about particle nature, sometimes we are talking about wave nature, but where, what we are seeing when we are like in photoelectric effect, you are seeing purely the particle nature of light. In black body radiation, you are seeing the purely the particle nature of light. But in interference experiment, you are seeing the purely the wave nature of light. And de Broglie that every particle has a wave associated with it. Then Heisenberg told them, okay, if a wave has a particle associated with it, then what phenomena should be observed when? So Heisenberg came up with his uncertainty principle, and the fundamental of this, say if you have a momentum of a particle given as lambda by h. So if you have a wave, a frequency, a single frequency wave or single wavelength, then what you see, if in space this wave will have a continuous amplitude at all points in space. So what will happen, that at all positions in space the amplitude is constant. So if we have a pure wave, if some phenomena is associated with pure wave, then pure wave will have same amplitude throughout space. So what will be? It's the position of the particle will become completely uncertain now. If we treat with a single frequency wave or single wavelength wave, and which means that the momentum, which is given as lambda by h for a particle, for a photon of light, momentum is given as lambda by h. So if the momentum is certain means if the wavelength is certain, then we don't have any information about the position. The position of the photon will become completely uncertain. But what happens if we superimpose many waves of different frequency? So of different frequency, smaller to higher frequency, if we superimpose, we get a wave package. So what we do, we superimpose a large range of frequency. The bigger the range of the frequency, the smaller will be the width of the package. The width of the package in space will become smaller and smaller. So what this says, that the more uncertain you are about the wave, about the wavelength, that the delta lambda becomes more uncertain. With the delta lambda, what becomes uncertain is the momentum of the light becomes more uncertain. You are more confining the light into a space, then the position of the light will become more certain. So when the frequency is well known, momentum is well known, the light is behaving ideally as a wave, practically as a wave, pure wave. But when you have a superposition of infinite number of frequency, then light will be confined in space, but its position will become certain, but its momentum will become completely uncertain. So this is where the Heisenberg uncertainty principle come up. So what it says in practical, it's physical, that if you observe a particle nature of a phenomena, if you observe the particle nature of light, you won't be able to see the wave nature of light at that. Or vice versa, if you observe the wave nature of light, where the momentum becomes certain, then you won't be able to restrict your particle. Where the particle is, you don't know. So the particle nature will become completely uncertain. So you can at an instant only observe one property of light. Though light may be having a duality, it will be having both the wave character as well as a particle character associated with it. But at an instant, and the explanation from Heisenberg principle tells that we will only be able to view one character of light, which will be either the particle character or the wave nature. So if we are able to observe the interference pattern, we won't be able to observe the particle nature. But if we are able to observe the particle nature, then we won't be able to observe the wave character. So one, like, if we whatever one nature, whichever becomes dominant, it supersedes the other nature. So, and this is can be seen from the photon strike, the double slit experiment. If you let the photon strike the slits, the double slits, and you don't measure from which slit the photon is striking. So, if you let the photons strike the slit and the experiment evolve over time, leave the experiment, then you will see the wave nature. You are not restricting the position of the particle. You are not fixing the particle, you are leaving the system to evolve. If you leave the system to evolve, you will get the wave nature. But if you observe from, try to observe from which slit the photon is going. So to know from which slit the photon is going, you have to strike the photon with another photon. So whatever this perturbation will completely destroy the wave nature of light. So if you are able to observe, and you will be able to, if the wave nature is destroyed, what you get, you will able to see it for the two slits only to position the particle. The light is going from the two slits, the particles are going from the two slits. So if you interfere with the system, try to observe the particle nature. So what you will be able to only observe the particle nature of light. You won't be able to observe the wave nature of light. But if you leave the wave to or light to evolve, the system to evolve on its own, then what you know from the quantum picture, the Schrodinger picture of light, which we have a Schrodinger wave to explain the probability, the system will evolve as a wave in the Schrodinger picture. So this is how the evolution of the theory of light came to the present stage, and this is an experiment like to just demonstrate the quantum nature of light, how the phenomena quantum can give rise to like more secure or better communication. So suppose we start with, we have a sender and a receiver. So we have Alice and Bob. Alice wants to share a important message with Bob, and both are miles away from each other. So what happens? All of you know that a system, a quantum system, if you leave it will evolve on its own. But if you perturb a quantum system, then the state will change. Its state will change when you perturb it. So in the classical picture, like when we measure quantum system exhibit, so when measured the quantum system, if you perturb it or try to measure the quantum system, it exhibits a particle nature. The measurement that acquires information perturbs the quantum system. So based on this, if we let the Alice and Bob communicate using classical channels, classical channel may suppose an optical fiber. You have Alice and Bob connected to each other through an optical fiber, and you send information in terms of intensity of light, of laser light. So what could happen? Any person in between who wants to hack the information. Say here Eve want to hack the information. He can come up, he knows the fiber, He will just put a cut in the fiber, some information will come to him, and in the path after the cut, in the path of the bob, he will put a amplifier. So the intensity will get amplified. A part of the fraction intensity may come to Eve, but since the remaining signal is getting amplified, Bob won't be able to know, the receiver won't be able to know that the communication is hacked. But instead of a classical channel or instead of a classical mode of communication, if Alice used quantum bits, sends her information in terms of quantum bits. So what happens in terms of quantum bits, if Alice sends her information to Bob, if the Bob receives it, he knows that he has received it. But if Eve if any eavesdropper or any sort of hacker tries to get the information, what will he do? In the process of measuring the information, he will disturb the quantum system. And the quantum signal, like if the quantum signal is disturbed, state will be disturbed, then Bob will be able to know that the system has been hacked, that he is getting a disturbed signal now. So this is a way of securing your, knowing that your communication is secure or no. Classically, you won't be able to secure your communication, but quantum mechanically, based on the concept that any measurement will perturb the system, the nature of the system will be destroyed now. So based on this principle, this is the principle that which give rise to quantum key distribution or quantum teleportation, now, which is being presently used worldwide for military communication, for highly secure communication. We use now quantum bits to communicate so that both the receiver and the senders know that communication are secure, and if the communication has been hacked, then they know for surety that the system has been destroyed, has been perturbed, so they can discard the information. So this is the principle behind I gave you about the things about quantum nature and how light evolved, and what's the one of the basic present implementation of this quantum nature of light. Now, what are quantum bits and how we get quantum information? This is the thing on which my research is presently being involved. Like I'm presently involved in my research on the development of single photon sources, a highly quantum source of light where you have one photons coming out at an instant. So you have one photons coming out, it has a state certain. If Eve wants to get the information from the photon, Eve can't. Any Eve or any hacker won't be able to break the photon into half. He will be able to detect the photon completely, so the photon will be lost from the system. He has to send another photon, but the state will be different. So you can't hack a single photon. So if you convey your information in terms of single photon source, you won't be able to hack the single photons. And my research is based on the development of highly bright single photon sources. So how to measure? Here in this slide, I want to show you how to measure experimentally the single photon nature of light of your source. And this is the basics of the experiments which we do in our lab, or we are planning to soon do in our lab. That's how we measure the quantum nature of light. So this is a simple schematic of what happens when you strike a light on a 50-50 beam splitter. Suppose you have a beam splitter and you strike your light on the 50-50 beam splitter, and you have two detectors, one along the transmitted arm. Detector 1 is along the transmitted arm and detector 2 is along the reflected arm. So if you have in the classical picture whatever dim, whatever dim the light signal may be, but it is represented as an electromagnetic wave. So it has a wavelength and it has a field associated with it. Corresponding to the field, it will have an intensity associated. So if you strike the light on a 50-50 beam splitter, what will happen? The intensity will be split equally into two parts. So what will happen? You will get simultaneous detection on both the detectors. What the light intensity just splits up into half, and it goes to both the detector along the reflected arm and the detector along the transmitted arm. But what happens when you strike the detector in the quantum picture where single packet of energy or photon is striking the beam splitter? What will happen now? To see this from the, like, what is photons? Or photons are packet of energy. When they strike the beam splitter, what we say that the system could go in any direction. The probability of it, if you treat it the packet of photon in terms of Schrodinger picture, then the probability, the wave function will be equally split along the two directions. You have a wave in the Schrodinger picture striking the beam splitter, the wave function will be split equally in both the directions, and the wave function will go equally in both the direction. The amplitude wave, the wave function probability will go exactly in both the direction. But the event of detection, when the detection happens in either of the detectors, say, either detector 1 or detector 2, what happens when you detect it? You detect the whole photon, the whole probability, and the collapses over that point, over the detector. So if you detect the photons on detector 1, you can't detect the photon at that instant in detector 2. But before detection, the probability is same for both the detectors. But the detection event will collapse all the probability at that detector point itself. So when you study the correlation of the photons striking both the detectors in terms of number of photons or intensity, which is field square, and in terms of number of photons striking both the detectors, you will see that the number of photons striking both the detectors for a single photon source, and if you study the correlation, you will see when one photon is striking detector 1, you can't get a photon in detector 2. So the correlation, if you study between the detectors, at time instant, at same time instant, will always be 0. The amplitude of detector 1 multiplied by 0, because the probability of detection on detector 2 is 0. If it's the probability of detection on detector 1 is 1, it becomes 0 on the other detector. So what you see for a pure quantum source of light in terms of photons, the detection will collapse all the probability. And if you measure the intensity correlation function, the correlation function of the two detectors, of the detection events on the two detectors, you will see for a single photon source when n is equal to 1, at the same instant, the probability, the G2 function should go to 0, ideally 0. The cross correlation between the both the detectors should go to 0 for an ideal single photon source. But what happens to the thermal source when you have, normally classical sources are thermal bright sources? So you have a electric bulb, a thermal bulb. You have bunch of photons coming out from it. So if you measure the G2 tau experimentally, it's higher than 1 and even around 2. For a very well-known classical source of light, which is laser light. Highly monochromatic, highly coherent. Ideally, a laser light is ideally coherent source of light. The well-known has a, if you see the emission of photons, it follows a Poissonian distribution, the random walk problem. The Poissonian distribution. So for even for that classical source, the G2 function goes as is exactly equal to 1. But for a pure quantum source of light, And each photons of four pure quantum source of light is known as anti-bunch. Means all photon events are well separated in time. All photon emission events are well separated in time, so you get only one photon at an instant. So our ideal single photon source is highly anti-bunch, and the G2 tau value or G2 zero value at same instant is always ideally zero. So if we measure experimentally for a source G2 value to be zero, we know that it is a single photon source. So this is what I'm doing in my lab, and from the PhD time, I'm working on the development of single photon source, characterizing what single photon sources are. I'll give you a brief idea about one of the sources. Like here are few applications I have of single photon sources. All of you would be aware about National Quantum Mission, the evolution of quantum technologies, like how the world is progressing towards quantum technologies. So what are the application of this sort of single photon source? It is application in quantum cryptography, in quantum communication, in quantum computation, quantum computers. All this single photon source will become a basic building block of. So, so these are the features I have highlighted here. What are the ideal features? What you look like if you want an ideal source, single photon source, and which what we are trying to develop in our lab and in the world right now, an ideal single photon source. So what it should have? It should be highly anti-bunch. We know it should be having single photons emission at time, but it shouldn't be highly bunched. For communication. You require the information to convey a lot of information with time. You are now using internets with speed in gigahertz, in gigabits, megabits and gigabits high speed internets. So you require this photon emission to be in for practical application, to carry information, to be in the brightness or the photon count rate, emission rate, photon coming out should be in the order of gigahertz. So you have giga number of photons coming out per unit time. So your source need to be highly bright. Other things that your source need to be stable. If you have a source, you want it to stay there for years or months at least. It won't lose it. Like it won't lose a bulb which get loose after some time or which is lost. We call it a faulty bulb. So for communication, if you want to deploy a source, you want the source to be highly stable. There shouldn't be any blinking in it, any bleaching. It shouldn't die down with time. Plus, you want it to be controllable. You want to get the photon only when you want the photon to come. So you want it to be controllable. You want to trigger. You want to get the photons on demand from it. And then if you want to use it for quantum interference experiments, so you require the photons which are coming out. All photons should come out, should be highly coherent to each other, should come out in same mode. They should be having the same frequency, the same momentum. So all photons should come out in the same mode and in phase with each other. So these are the practical, and presently one of the well-known sources for this, and which I worked on it in my PhD, is the well-known nitrogen vacancy center in diamond. So nitrogen vacancy center is nothing but, all of you know, in diamond we have carbon bonded in, carbon atoms bonded in tetrahedral form, sp3 hybridization. So each carbon atom is associated with four carbon atoms, and it has a valency of 4. So each carbon atom will have 4 electrons. It will make bonds with 4 other atoms. So what happens? Nitrogen, if we have during the formation of carbon or during the formation of diamond, if we have some sort of nitrogen gas present from the atmosphere, what will have? Nitrogen has a valency of 5. So if it gets bond to two electrons, there will be a valency remaining close to the nitrogen atom. Though it has deficiency of 3 electrons, 3 electrons will form bonded with it, but still a valency with the carbon will remain. So a vacancy will come up and you have an atom nitrogen vacancy center, a defect center being formed. And this defect center, when it is excited, its emission is in the visible region. It is zero photon line, the emission line around 637 nanometer. And this is the room temperature emission spectrum. The width is coming in the emission spectrum is coming due to the room temperature, the phonon side bands which are associated with it at room temperature. When you go down to zero to nearly liquid helium temperature, it becomes narrower and narrower, the zero photon. So this diamond is known to be a very stable source of light. So the weaken the impurity center, its force will also be very stable. So it's known to be a stable source of light, well-known source of light, and it's used in many like quantum technology application. It's used as single photon source in quantum technology. Plus, due to its stableness, because diamond is known to be one of the most stable system right presently. So as a nano diamond, it could be used because there is no, it's a stable source, no blinking or bleaching happens. So it could be used as a biomarker or labeling applications in biology also. And if you are able to isolate a single photon, a single vacancy center, this NV center from the previous diagram, if you see, it has a triplet state. You have a spin 0 plus minus 1 state, and it could be like this triplet state could be excited with the external magnetic field. And even for single atom, it could be excited, it could be sensitive. You could have Zeeman effect from the magnetic field of very small, of another tiny atom close by it, having a magnetic moment. So it could be used as a magnetic field sensor, highly sensitive, single atomic level sensitive magnetic field sensor, also magnetic field sensor. So these are the applications of these NV centers presently, and it's very well established presently single photon source right now. Now, and here to know the single photon nature, you, as I told you, you measure the G2, the second order correlation function, and you see experimentally, if you observe from this source, you see that the G2 zero value goes very close to zero value. Experimentally, you have some background noise, so non-zero value is associated with the zero background noise. Some experiments where the background is reduced, it's been found that this G2 tau value goes exactly very close to zero. So this showing that it's a single photon source experimentally, its emission, and then what's the lifetime. But here there is a catch. This is a very stable single photon source, and it's very stable. It's known to be a single photon source, ideally single photon source. It has a quantum efficiency very close to unity, so it's a triggerable. Also, you can get photons on demand. Also, whenever you excite it, you know when the system is excited to the excited state, its quantum efficiency of emission is very close to 1. You will get a photon out of it. That are all fine, but there is a limited here that it has a slow lifetime. It has a lifetime in bulk diamond medium of around 11 nanosecond, 10 nanosecond. So if you have a lifetime of 10 nanosecond, what's the data rate you expect it to be? 1 nanosecond, you expect the data rate to be 1 gigahertz. 10 nanoseconds, the data rate, maximum data rate, if you are able to collect all the photons, will be 100 megahertz. And since like the emission from a dipole is sinusoidal, it's not well directed in one direction. In general, from using a lens, what's been detected is only around 20-30% of the radiation. So the maximum data rate you can get is only few million counts per second from this. So because of this, the low data rate, it's lacking in practical applications. Presently lacking in practical application. Now, how to increase the number of data rate? Increase the number of photons coming out from it. So presently, theoretically, what we make use of to increase the data rate, what we make use of quantum mechanically, for any transition to happen between a two-level system, say from state 1 to state 2, of say I here corresponds to the initial state where the system is. Say initial state corresponds to the ground state, and F corresponds to the final state. So if from Fermi's golden rule, what says that to transfer an atom, transfer a system from the initial state to the final state, you require an interaction Hamiltonian. So your interaction Hamiltonian acting on the system will trigger the system to move from the initial state to the final state, and the rate of this transition is given in terms of the density of states, that the number of corresponding to this transition, the energy difference between the initial and the final state, that how many possible energy states you have, the density of states. So more is the number of density of states, more will be the rate. So this is how, like, if we can increase the density of states, we can increase the rate, and this is how presently the physics is evolving in diamond center, that we can control the density of states based on this Fermi's golden rule picture. So I'll show you for optical transitions, radiative transitions. And now we know this is the equation of radiative transition. What's the Hamiltonian here? It's the D dot E, dipole moment dot electric field operator. The external field which acts on the dipole give rise to the transition, and the number of states, the summation is over the number of states. So you have the system in the ground state. If we have a coupled system, atom and light coupled system, so what you have in the ground state, you have the system in the ground state, but there is no photon at it. When the system, when the nitrogen vacancy center is in the ground state, or any two level system is in the ground state, you don't have any light emission from it. But what happens when the system is in the ground state? There's no photon out of it, but fine. This is the transition operator system from the initial high level to the ground level. So, but when the system is in the final state, E corresponds to, I was sorry a bit, E corresponds to the excited state and G corresponds to the ground state. So initially we are treating in this that the system is in the excited state, the electron is in the excited state, and there is no photon coming out of it. The photon comes out of it when the electron moves to the ground state. When there is transition happens to the ground state, and a photon of energy corresponding to the energy gap of the system from the higher state to the lower state, that energy gap, a photon will come out from the state. So initially the system is in the excited state, no photon. Finally what happens? You have a system in the ground state, comes to the ground state, but with a one photon. And this photon which comes out could have any of the, say, polarization could be anything. It could be polarized along any direction electric field, and it could be momentum along any associated direction. So you have a in a free space, all directions are equivalent. So your momentum could take any of the directions. So number of states in terms of one for the photon to come out are larger. So you can control the number of final states by controlling the number of photons which are coming out from the state. How many states are possible? So if there are more number of states where the photon could come out, what happens? The summation increases, and the rate of transition will increase. If you have less number of final states, the rate of transition will be less. So this is the principle behind how we can tune the number of rates or the rate of transition, or make the system more brighter and brighter. So this is how, from the Fermi's golden rule, the density of state picture is rho omega. Then you have the D dot E operator, the final state and the initial state. In the classical, quantum efficiency is considered to be 1. So what happens when the field interacts with the atom? What you get transition. So we can tune this density of states using different modes, like we can use plasmonic resonators where you have plasmonic resonances, free electrons, a huge number of free electrons present there. If from the free electrons the light could couple to these number of free electrons, you have large number of free electrons available, the photons could couple to any of these free electrons, the number of k vectors is large, enormous. So you can increase the density of states through this plasmon modes. You can use photonic cavities to increase the density of states. You can use many other resonators sort of to increase the density of states. So if you have NV centers nicely coupled to any of these resonators, you can increase the photon count rate from those. So these are the principle behind increasing the density of states. And this is the experiment, how we measure the experimental setup, which we are now developing here. Almost we are done. So what happens, like, to excite the emitters, you have a sort of sample holder where you have nanodiamonds placed on the cover glass experimentally. You excite the sample. You have to first make the NV center move to the excited state. Then only when it comes back to the ground state, it emits one photons at a time. So say if you are able to isolate one NV center, you will get one photon at a time, a nice single photon source. So to excite this source, you require a laser, which is we use a 532 nanometer CW laser, continuous wave laser. Then you have a objective lens to focus the light on the sample. So when you excite them, you excite the sample, the emission of the light, you collect it using the photon detector. Then you will, to remove the laser from the emission, the laser will also be reflected back from the sample, from the glass. So to remove, you use filters. The notch filter will remove the laser and will only pass the emission from the NV center. So you use you have now, to the emission, you can you can measure the spectrum using the spectrometer, or you can measure the time correlation, the, as I told, the G2 function, the second order intensity correlation function, using these two detectors, the beam splitter and two detectors along the reflected and transmitted arm. So this is what we do, and this is the experiments I'm doing presently now, working on it. So this is all from my talk which I have, starting from the basic of what photons are, the development of the understanding of photons, and what we are doing presently in our labs. So you're open to questions now. If you have any questions, any queries, all of you are welcome.
Thank you so much for this wonderful talk. So participants have few questions.
The emission of a photon from the quantum system uncertain. Just it affects the emission of photon from any quantum system is governed by uncertainty principle. First, like, talk about emission, how emission happens. Emission happens when you have a system in the excited state. So you have a system, a two-level system, like simply speaking, consider two-level system, an atom in the excited state. So when will the emission happen? The emission will happen when it interacts, when a Hamiltonian trigger it. Like, all of us know that all these energy levels where the system resides are stationary levels. So if the system is in any of the energy level eigenstates, these are stationary levels, are also known as eigenstates. Energy, if the system is any of the eigenstate, it will stay there forever until and unless it is perturbed. There is a time perturbation happening, then it will evolve with time. So what happens if you perturb it with a field? You have a transition operator which is d dot E. If you perturb it with the transition Hamiltonian, what will happen? The system from the excited state will drop down to the ground state. And this dropping down of the system from the excited state to the ground state will result in the emission of energy. If the emission is radiative, if you have radiative emission, if the quantum efficiency of the emission is 1, we have purely radiative emission, then the energy is emitted in terms of photons, a packet of energy called as photon. But if you have non-radiative emission, non-radiative means the energy is instead of coming out as a photon, is lost within the lattice, within the phonon lattice, and it results in phonon vibration leading to increasing temperature. So system, whenever it comes down to the ground state, it could either emit a photon corresponding to radiative transition, or it could lead to phonon vibrations, increase in temperature. eh, So the energy has to come out. So it depends on the quantum efficiency of your system. Higher, if you make the quantum efficiency, if the quantum efficiency is close to unity or exactly unity, you will get one photon exactly from it. So you will have a controllable system only when you have the quantum efficiency to be unity. If the quantum efficiency is not unity, it's very small, then it will probabilistic. You could get a photon out of it, or you could get a non-radiative transition. But a transition will happen. It could be either radiative or non-radiative.
We have another question.
Uh, Photon is massless when it is at rest. When it is moving, it has a momentum and it is a mass state. So it's a nice thing that photon is massless, but only when a photon is at rest. For an electromagnetic wave, the light is moving and photon is traveling. It has a momentum, so photon is not massless when it is moving.
Sir, I also have one question.
Yes.
You talk about quantum communication that is more secure and for especially for military purpose.
Yeah.
When two person like Alice and Bob share the key, so if someone will try to break the communication, so they will came to know. But there is one
Yeah.
more thing, super dense coding, and super dense coding perhaps called more secure than the quantum teleportation. So could you
It
please
may be,
get
but if it is a classical thing, then classical thing, if you consider communication in terms, I don't know much about super dense coding, but any classical system, if you consider classical system, say photon, any classical system, there is nothing that the state will get perturbed when you measure it. But from quantum, the basic quantum nature is says that when you measure a quantum system, you are perturbing the system. So quantum communication is based on this principle that the system is getting perturbed, and since the system is getting perturbed, you surely know that the system has been hacked. So this quantum nature principle is giving rise to the security in the communication.
okay, sir. Thank you very much, sir.
I also have one question.
Yeah.
So, can you please make some comments on quantum dots in the context of single photon?
Quantum dots. If you can isolate a single quantum dot, a single quantum dot. So what you, if you have isolated your energy levels, you have isolated in all dimensions. Its dimension is zero. So your energy level will be very well discrete and well separated. So if you treat the transition is happening between any two energy levels, so you have a nice two-level system happening. So if you are able to isolate one single quantum dot, the emission from it will be a single photon source. You will have only one emission, one photon coming out from it. To get the other photon, you have to again excite the system to the excited state. Then when it drops down to the ground state, you will get the second photon. So between them, you have a difference between the transition time or the lifetime of the system. At least it will be
Okay.
separated, but the photons which are coming out will be separated by this. So if you have an ideal quantum dot, a single ideal quantum dot, it will behave as a single photon source.
Thank you so much for this interesting and informative talk. So, let me invite Professor Shamin Ahmed Siddiqui, Head Department of Physics in Trigger University, to deliver the vote of thanks.
Thank you very much, Dr. Shah Alam. So, first of all, I would like to extend my gratitude to the top leadership of the Integral University, that includes our Honorable Founder and Chancellor, our Honorable Pro Chancellor, our Honorable Vice Chancellor. Then I'm also grateful to Dean Faculty of Science and Director HRDC for their continuous support. And I'm very much thankful to Dr. Faraz that he discussed one of the most fundamental question of physics, that the nature of the light, and the way he explained. Uh, he started from the corpuscular theory of the Newton, and he uh, touch almost entire spectrum of the light. So he explained in such a beautiful and elegant way the the character of the light. So I'm very much thankful to Dr. Faraz Ahmad
Thank
Imam. And earlier we were trying to schedule this FDP in physical mode, but due to some important thing like that, we are approaching to the semester exams. So we converted it into the hybrid mode. So next time I will request Dr. Faraz to visit Integral University so that we can get maximum benefit, our faculty member, our research scholar and students from his excellent work in the forefront of quantum optics. So thank you very
thank you,
much,
sir.
Dr. Faraz.
Thank you, sir. Thank you very much. It will be my pleasure to come over there. I'm looking forward to it.
Sure, sure, sir. We will invite you very soon, sir. Thank you, sir.
Thank you. Thank you.
Okay, sir. Thank you so much.
Okay, Shalom.